Okay, thank you for the introduction. I'll be talking to you about probing trillion-degree matter. So it turns out that most of the matter in our universe is nowhere near trillion degrees. The hottest matter in our vicinity, the core of the sun, is about 1,000,000 degrees. So why would we want to study something that is 1,000,000 times hotter than anything we're bound to encounter? So it turns out that shortly after the Big Bang, the entire universe was actually this hot. And it only up to about a microsecond after the Big Bang, which may seem like a short amount of time, but only up until then was the universe, after then the universe was cool enough to be able to see matter in the way that we know it today, in the form of protons and neutrons. So we can learn a few things about how matter behaved back then to try to understand how our universe came to be. And we can also learn a few things about the strongest force in nature. So there's 4 forces in nature: gravity and electromagnetism, which we are the most familiar with; the weak force, which is relevant in nuclear processes; and force, which is so strong that it's almost not relevant. So the strong force is the reason why the nucleus sticks together even though it's all positive. But other than that, it doesn't seem to do much. And we see from the electric force, for example, because you can get ionized things, because you have chemistry, because electrons can flow, you have a lot of very rich physics. In fact, it's the reason why we have life in the first place. But if you were to make the electric force 100 times stronger, then you would never separate the electron from the atom, and the universe would be a very boring place. So that's the state that the strong force is in right now. But if you can heat up matter to 1,000,000,000 degrees, then you can start to see it behave much more richly. So just to review, protons and neutrons, which make up most of our stuff, are actually not fundamental particles. They're just a bound state of quarks, the same way an atom is a bound state of an electron and a nucleus. So if you heat up matter enough, you can actually start to melt these protons and neutrons into what they're made of. So we can't recreate the Big Bang to get this type of matter, but what we can do is we can collide lead nuclei very close to the speed of light. Any heavy nucleus will do. And when you do that, most of their energy will get deposited in a very small volume, and then you'll get this new form of matter, which we've called a quark-Gluon Plasma. And this is where quarks and gluons, other fundamental particles, can freely move and interact with the strong force to their full potential. So let me show you a short animation of such a collision. But before I start, some things to note are the sizes of these objects are the size of a nucleus. So this is very small, a few femtometers across. Secondly, nuclei are generally spherical, whereas these guys look like pancakes. And this is because they move so close to the speed of light that relativity has contracted the sphere into a disk. And lastly, take note of the time scale here. This is femtometers per C. So this is the amount of time it takes light to travel 1 femtometer, which is about 10 to the minus 4 seconds. So as I play this animation, if it works, the red will be the quark-Gluon plasma. And notice how little it lasts, just a few femtometers over C. All this gray matter here is just regular particles as we know them, as they spread out from this collision. And you see a bit of quark-Gluon plasma left on the edges due to time dilation. And as you zoom out, all these particles will stream out in all directions from this explosion. And now you want to detect them to get an idea of what's happening. So to make these collisions in the first place, you need a very big accelerator. There's a very nice one near Geneva on the border of France and Switzerland called the Large Hadron Collider. So there are some mountains here for scale. This is 5 miles across, and it's about 100 meters underground. And this is capable of accelerating lead nuclei and protons to very, very close to the speed of light. And the way it works is you have 2 beams, one going clockwise and one going counterclockwise, close together in the same ring. And then these beams will intersect at collision points, where you get these collisions and try to detect them. So the experiment I work on, called CMS, is located right here. And it looks something like this. It's called a compact muon solenoid. And even though it's compact, it's about still the size of the cathedral. Here, this little gray person is me for scale. And the things to note about this detector is that it completely surrounds the collision, so it gets almost all the particles that come out. There's a 4 Tesla solenoid, which is a really strong magnetic field that will bend all charged particles that try to move through it. And then we have a few ways of tracking the trajectories of those particles. We have this thing called a tracker, which is like a computer screen wrapped around. And each time a particle goes through one of the pixels, it'll register a dot right there. And if you have enough of these, you can try to connect the dots and get the trajectories of these particles. Then we also have calorimeters, which measure the full energy of a particle that hits them. It gets converted to an electrical pulse that is higher the more energy the particle has. And with these tools, we can start to measure the particles that will come out of this Quark-Gluon plasma. So here is what a collision looks like. On the left is a collision between 2 protons. All these spaghetti lines are their trajectories as reconstructed from the tracker. And some of the Legos here are the energy deposits. So you'll notice some very funny math. So here we started with 2 protons, and then out come hundreds of particles. Likewise, here we have about 200 protons and neutrons in a single nucleus, and out come 30,000 particles. So how can this be? And it turns out E equals mc squared plus quantum mechanics lets you have this. So E equals mc squared is why nuclear reactors, for example, give you energy. They convert matter into energy. Here, the opposite happens. You have a pair of protons which together have 7,000 times their mass worth of kinetic energy. And once they collide, you can make hundreds of particles from nothing, just using that energy. And this is actually the same way all the matter that we see around us came to be. So in the beginning, there was not matter packed into a small space. There was a lot of energy. And then by a similar process, that energy got converted into the matter we see today. So let's look at what we can learn just from looking at this picture of the Quark-Gluon plasma, of the explosions after the Quark-Gluon plasma. So we know the initial volume is around the size of a nucleus. And you can get slightly more accurate descriptions if you do some hydro, but it's around 10 cubic Fermi. The initial energy deposited there you can measure by adding up all these calorimeter towers. And then if you know the volume, you know the energy, you can calculate a density. And that density is around 30 GeV per cubic Fermi. So what does that number mean? Well, in terms that we are more easy to imagine, if you take something that's 1 million times the mass of the Earth, so the sun, and compress it into a ball the size of Manhattan, you get a neutron star, which is very dense. And that has about 1 GeV per cubic Fermi. So the matter we create here is around 30 times denser than that. And it's also, from simulation, you can extract the temperature, which is around 4 trillion Kelvin. So now that we have created this matter, what are some ways we can study it? You saw on the previous slides that there are thousands of particles created per collision. So one way to do it is to study correlation between those particles. And we have done that, and we've discovered some very interesting properties that this matter behaves more like a fluid, even though it's called a Quark-Gluon plasma. We named it before we created it, so we got some surprises there. And more recently, at the Large Hadron Collider, we discovered that you can have relativistic hydrodynamic behavior in systems smaller than ever thought possible. So even in a pair of protons, if you pack energy tightly enough in that collision, you'll start to see some hydrodynamic behavior, which was not expected or expected before. But it would be nice if we can probe this plasma the same way plasma physicists will shoot some beam through a normal plasma. However, it's very difficult since this lives about 10 to the minus 23 seconds and is the size of a lead nucleus. So we can't shoot something at it externally. However, we're lucky that nature, if we work hard enough, will give us a pair of probes. So in a few collisions, not very many, you will have a pair of back-to-back particles be created at very high energy. And just like when you collide two billiard balls, they go with opposite and equal momentum. These back-to-back particles start off with opposite and equal momentum. However, as they traverse through the Quark-Gluon plasma, they can get created, they may not necessarily be created at the center, they can be created off to a side. And they may lose different amounts of energy. So when we look in our detector, we don't see these back-to-back pairs of particles, since they will, using the same mechanism as the rest of the collision, convert their energy to surround themselves in an envelope of other particles. They will show up as a collimated spray of particles called a jet. So in a small cone, you'll get a lot of energy, and we know that this corresponds to the initial particles. And it is true that the sum of the energy in this cone is equal to the total energy that the particle has when it comes out of the Quark-Gluon plasma. So you will see that these towers may not be the same height. However, probing it in this way has an intrinsic limitation, which is that we don't know the initial energy of these probes. We can only measure them at the very end. So it would be nice if we can somehow know the energy that they started out with. So even there is an even rarer probe where instead of a back-to-back pair of quarks, you have one of those quarks gets replaced by a photon of equal energy. And the nice thing about that is that photons do not interact with a strong force, so they will pass through the Quark-Gluon plasma unhindered. They will lose essentially no energy as they come out. So when you measure, and they will look in your detector as one very tall tower of purely electromagnetic energy. So then now you finally can know the initial energy of your probe, and then the one on the other side, which loses energy, you now know exactly how much energy it lost and can do a lot more precise studies this way. So because these events are so rare, you actually, the computational side becomes extremely important. So the LHC will produce collisions about once every 50 nanoseconds. And if you look at there are thousands of particles being created. Each of those particles corresponds to a dot, which means millions of channels of information being read out every 50 nanoseconds. You would end up writing a 1 terabyte per second to disk, which is not feasible. And it's also very expensive to store anything close to that. So what we do instead is we trigger. We throw away most of the collisions and keep the very few percent that are the most interesting. And the way we do that is with a combination of hardware algorithms and software algorithms. So the detector is read out. You have some pulses of various voltages of various heights. Those are digitized. And then you run those through some logic gates, which can do very simple computations, but do it very quickly. So for example, you can ask, is there a high enough tower of energy to maybe indicate that there is a probe? And you can calculate that in a few nanoseconds, which is enough time before the next collision comes in. And then if those basic but fast algorithms let a event through, then it gets passed through a processor farm of around 10,000 computers, which will run more complex reconstruction of the same type that we use to study these events offline, to run, for example, clustering to see if you have a full jet or just some random spike, as well as other things. So after you do this and keep just a few percent, you're still left with about 1 petabyte of data after just a month of running. And that's a lot of data, but we're lucky that it parallelizes very easily because every collision is independent from every other collision. So as long as you have a network of computers that have efficient many-to-many read and write, then you're good. And we have that in the LHC computing grid, which runs on top of Hadoop. So that's good. And in fact, we now, so since 2015, the LHC turned back on again at double the energy and a much higher collision rate. And we went from having around 1,000 of these photon plus quark collisions that are the best ones to having around 150,000 at the end of last year. So now we can finally do some real physics with these probes and really try to understand how particles moving through this matter lose their energy. So yeah, that is what I'm working on now. I'd like to thank Krell and the DOE CSGF to give me wonderful opportunities to go to Berkeley to study relativistic hydrodynamic theory and to meet everybody here. And I'd also like to thank my collaborators and MIT for giving me the opportunity to work on this research. Thank you.